joining our conference. So
Yes.
she is from Monash University in Australia, and she's going to speak about familial inference. So I have to make you co-host just
Okay.
so that you can share your screen.
Okay.
All right. Yeah, I made you co-host. You should be able to uh, share your screen.
Can you see that?
Yeah.
And can you hear me? You can hear me too. Good. I've got a bit of a croaky voice, so I apologize for that. Thank you very much for the opportunity to speak to you all today. I had thought that this time would be really good because being in Australia, this would be nice, but I'm actually in Montreal at the moment. So things got a little turned around on me, but I'm still very happy to be here. So thanks very much, and hope to join some of the other sessions from today. So I wanted to speak about this work that I've been doing recently. It's called Familial Inference, and it's joint work with a few people. So I've got here on my slide, Ryan Thompson. He's one of my PhD students at Monash. He's actually just taken a position at University of New South Wales, and he'll be submitting his thesis imminently. And the other two collaborators are Steve McEachern and Mario Perugia from Ohio State University in the US. And Steve and Mario and I have a National Science Foundation grant, which I want to acknowledge today as, thanking them for that support. So familial inference is a new thing. It's something different. And so I'm excited to share it with you today and get your feedback on it. Okay. So got a bit of a roadmap here, just to give you an idea of where we're going. There's a fair bit. The paper is actually available on the archive, and I'll give the citation at the end of the talk. And the talk essentially kind of goes through a similar order as the paper if you're interested. So it's really about hypothesis testing. But it's not sort of your standard Neyman Pearson frequentist hypothesis testing. We're thinking about hypothesis testing from a Bayesian perspective. And moreover, we're thinking about a different way of conceiving the kind of hypotheses that we want to assess. So let's start with that. Whether you're thinking Bayesian or frequentist, statistical inference is just widely used in many different. Is everything okay?
Professor Forbes, can you put it into a view presentation mode so that it will? Yeah, no, great, thanks.
Yes, thank you. Good suggestion. Yes, so whether you're thinking Bayesian or frequentist, the process of considering hypotheses from a statistical perspective, really, it starts with a scientific hypothesis, which comes from some discipline outside of statistics, generally speaking. And then we have to translate that scientific hypothesis into some statistical version of it that we are able to test. We then go ahead and undertake the test. These are the two circles in the middle. And then at the end, we still have to then convert that statistical test to a scientific conclusion. And of course, there's some discretion that the analyst has about how that takes place. Ideally, you'd be working with, people from other disciplines, and they have an understanding of what a statistical hypothesis needs to be. And, there's good interaction that can occur around these discussions. However, I want to restrict to just the consideration of hypotheses around the center of a distribution, and we'll call that center mu, say. And you might think mu could be a mean, in which case you would translate your scientific hypothesis from the center of a distribution in some context to formally the mean of the population in your statistical hypothesis, undertake a t-test, draw a conclusion from the t-test, and translate that back to the center of the distribution in the context of the scientific study. Of course, it doesn't have to be a mean. It could be a median, in which case you do a different test, and there are a few choices. It could be some other measure of center of the middle of that population distribution. For example, you might want to consider trimming some of the observations if you're concerned about outliers. You may want to downweight some observations if you think that there's good reason to do so. In which case, you would change your definition of what mu is, the population quantity that you are assessing, and then undertake the relevant statistical test before you reach your scientific conclusion. So there are actually many different measures of center that we could test, and it is a decision which one to test. And of course, there's often not much guidance in the scientific area as to which center would be the most relevant one. Or indeed, if there is only one, maybe there are more than one. And how, do we even consider that when we're in the process of making that translation to the statistical hypothesis? So what we argue is that that transfer from the scientific hypothesis to the statistical hypothesis is really a subjective decision that we might reach consensus about, but then again, we may just use a choice that is convenient for some other reason. So there's some possible gap then between scientific motivation for that choice and in fact some other motivation, and it's rarely ever considered in our discussions, in our, what we report in papers. And of course, this ties into the whole reproducibility issue in science. You can sort of cherry pick the type of test that's going to give you the result that you want in some cases. We've kind of got methods to counteract that to some extent, but it still doesn't, there's still a question about how do we do this translation? What's the best way? Is there a way that we can really think about our testing procedure so that we don't have to make such subjective choices in the process of, defining our hypothesis test? And this reproducibility issue or this subjectivity question, it's not just, in finance. It's not just in economics, although it certainly is in those disciplines. Marketing, any, psychology, any of the social sciences. It's also true in, physical sciences, biological sciences, medicine, anywhere where you're doing hypothesis tests, which arguably is, hard to find fields where they don't think about wanting to, use evidence to draw conclusions. So this is something that is really, it could have a great deal of impact. And it's a question that a lot of people in different disciplines are thinking about, and I think will continue to think about. Okay, so let me tell you a little bit about familial testing. So what familial testing is trying to do is think about not just a single measure of center, but rather a whole range of possible centers, population characteristics, which one might reasonably want to consider for your test. So here's just a simple data set that's widely available. You can find it in R, for example. And the question that we're just going to ask for illustration today is, do mammals tend to spend as much time sleeping as they do awake? And the data that's reported here are the ratios between the amount of time that the animal sleeps relative to the amount of time that they're awake across a wide range of different animals. So the distribution of the data, you can see, is quite skewed. And so there's some question as to what the center might be. Of course, you can think about a t-test, which would test the mean, and that's legitimate, at least asymptotically, right? So that's commonly one that people might consider. You might be more interested in a median, given the skewness. You might think a median is a better assessment of center. But of course, you can do them both and see which one gives you the result that you'd like to report. In this case, if you did a t-test, you get a p-value of about 0.7. If you did a sign test for the median, you get a p-value of about 0.03. So you'd reach different conclusions. So what we need are transparent tools which instill some confidence that we're not doing any of that cherry picking, which maybe is motivated by non-scientific desires. Okay, so what familial inference does is rather than test a single center like a mean or a median. It actually tests a whole collection, a family of plausible centers. So the word familial stems from this idea that we're going to test a family of plausible centers. And it's not a finite set of plausible centers, it's actually a continuum of plausible centers. So that's kind of, I guess, arguing why we need a different word here. So we study, in particular, a family of centers as defined by a Huber loss function. And if you're familiar with, Huber loss is in lots of different areas. Basically, it's a mixture of a squared and absolute loss as controlled by a parameter lambda. So you choose the value of lambda, typically. And if you make lambda equal to 0, you've got absolute loss, in which case the population quantity you'd be thinking of is the median. If you let lambda go to infinity, then you're talking about the population mean. And in between lambda 0 into infinity, you get an entire family of different centers as characterized by this function mu of lambda. So our familial testing problem is the null hypothesis that mu lambda is in some null set, say maybe, I didn't say so, but for this data, a value of 1 would mean that mammals spend as much time sleeping as awake. So that's sort of the critical number we're interested in. So we might be interested in, is there any measure of center for which a value of mu lambda being 1 is plausible? So we're going to do the test under the null to say, is there any center of this distribution according to the Huber loss that matches the null value, say 1? And the alternative would be, no, there is no value of lambda for which the corresponding center is the null value. So this is a composite test. There are many different hypotheses here, infinitely many in both null and alternative. So the null hypothesis is that at least one member of the family is consistent with the null effect. The alternative is that there are no members of the family consistent with the null effect. And this way, this may not always be the thing you want to test, but this offers a different approach for testing, a whole range of possible centers and decide whether or not the data supports a value of, in this case, a center equal to 1. So how we do the test now, we need to talk about how it's built. It's a Bayesian test, as I mentioned, and it's based on a non-parametric model for the distribution of the data. It addresses certain flaws of that null hypothesis testing that we've already mentioned, and it ameliorates some concern over model misspecification by the virtue of the fact that it's a non-parametric test. So we don't specify a true population distribution. Instead, we put a distribution over the possible values of that distribution, the population distribution, using a Dirichlet process model. Now, in order to go from the model of the population to the actual mu lambda function, we need some pathwise optimization routine in which we can solve for that mu lambda path. And we have done that. And in particular, that algorithm is very fast. You can do it very quickly for reasonable data size observations. So we have an R package to do this. It's called Familial, and it's available on CRAN now. And we've set up the package. There are a few different functions in there, not a huge number at this stage, but the ones that we have kind of mimic some of the standard things you would do. So for example, if you want to test center, like I've been discussing, and maybe you want to do a one-sided test, then the format of the R function is like t.test would be. So it's kind of got the same structure. So it's very easy to do and it's very quick. So for this particular example, do mammals tend to spend as much time sleeping as awake? Well, remember we had a p-value of about 0.7 for the t-test and for the sign test about 0.03. What happens with the Bayesian test is we actually get a a function for what the data tells us is the mu lambda, but that's just a point estimate. Because we're working in a Bayesian context, we want to actually compute posterior probabilities associated with that true path according to the Huber loss function. So what I've drawn here is it's actually a functional box plot, which indicates that we actually have a whole, it's based on a Bayesian bootstrap, which I'll explain shortly. We get resampled values of these paths from the posterior distribution, and that enables us to get not just a point estimate of this curve, but actually a distribution around the point estimate. And so we can actually evaluate probabilities such like, you know, I mean, these shaded areas, it's not a whole, they're based on simulated paths. So what we actually check are how many of these paths that we simulate actually cross the value of 1, what proportion, and that we can convert any posterior distribution over the entire curve to a posterior distribution of corresponding to, you know, whether the curve satisfies some condition. So it's just a marginalization down to the quantity of interest, which is mu lambda over the entire value of lambda. In this case, we get probability that the null is true equal to 0.633. So that's what we would consider an indeterminate result. It's not strong enough evidence for the null, and it's not strong enough evidence for the alternative, at least under 5% loss or error in either direction. But what it does enable us to do is quantify how certain we are about those hypotheses. And this is consistent with a standard Bayesian testing framework when you're working with just, you know, simple population mean questions. You can do Bayesian tests that are analogous to the t-test or the median test. And in that case, it's not a whole family, it's just testing a single point, but you can set it up in such a way that you just look for the posterior probability that the null is true against the posterior probability that the alternative is true. So we do that here, defined by the way that the null is specified for the entire curve, the familial null. Okay, so that's the basic idea. Now let's see a little bit more of how it actually works. So the target of inference is this Huber family, right? We want to know the mu lambda for the true population. So that's why it's got that subscript 0 on it. That's meant to indicate the true population. And lambda is going to go between 0 and infinity, so it lives on the positive real line. So the population Huber path, which we call it, is defined to be the value of lambda that minimizes the expected loss around the center. So that where the loss function is defined by the Huber function. So this is what I was saying, that if you take different values of lambda, you go between squared error loss, where lambda is infinity, and of course, the population mean will minimize the squared error loss, and absolute loss corresponds to the population median. But depending on your value of lambda, there's a whole continuum in between 0 and infinity, and so we have a whole continuum of potential mu lambda curves. So just to give you some idea for some common distributions that I'm sure you're familiar with, if you think about a normal distribution, well, it doesn't really matter whether you have squared error loss or absolute loss or some other Huber loss for lambda, neither 0 or infinity, you always get the same center value, which is 0, centered around the normal 0, 1 distribution here. So the Huber path for a normal distribution is just constant. But that's not the case for other distributions. So for an exponential distribution, here it's just an exponential 1, the mean is not equal to the median. It's got skewness in that distribution. And so the Huber path will trace, so if you start at the mean, then on the right-hand side and trace down to the median, it has this kind of declining shape. Log normal is kind of a similar thing. It's sort of monotone, but it's got a more pronounced, I don't know how you describe that, but it's turns more sharply, if you like. And interestingly, the Poisson distribution, it doesn't really matter whether the distributions are continuous or discrete. This method will apply equivalently to both. The Poisson distribution, I think by virtue of the fact that you get these, discrete probabilities, as you change the lambda from infinity down to 0, you actually get that decline, but then it sort of jumps back up. So that's interesting that that happens. So if you were tracing these paths, if you knew the true distribution, you could look at these paths and make your conclusion about whether your null is true or not, or your alternative is true. Of course, we never see the truth. We don't know the actual distribution. So we're using a non-parametric method for describing our uncertainty in what that true population distribution might be. And so we can assess, given the data, how, what the probabilities associated with those curves would be corresponding to the null and alternative hypotheses. So the non-parametric model for the distribution is just a standard Dirichlet process model. This has been around for a while now, and it's really become the main building block for Bayesian non-parametric models, although there are certainly other things beyond Dirichlet process. It's really the workhorse of Bayesian non-parametrics at this stage anyway. And the way that it works is, you have this population distribution, you don't know what functional form it takes. And so since you don't know it, as a Bayesian, you put a distribution over all the possible shapes that distribution might take. And then, given the data, you define the data given this true population as being IID from that population, but the population itself, your knowledge of the population, is given a prior distribution, which is the Dirichlet process prior. And now the Dirichlet process has effectively two parameters. One parameter is this p pi, which is some distribution, like maybe a normal, or could be anything really, could be a uniform, could be whatever you like. And then there's another parameter, which is we're going to refer to as C, often called the concentration parameter, which describes your certainty or lack of certainty, the degree of belief in that p pi underlying model. So if you really convince your data are normal, then you would put a very strong concentration parameter, a high value for C. If you were uncertain of the true population distribution, you would choose a value of C, which is much smaller. So it's a relative thing. Now, what we actually do, and you could choose your C and your p pi and do the same familial testing in that case. We are not doing that in the paper, though, because there is this result which says that actually, if you take the limit as C goes to 0, then the posterior distribution, which when C is not 0, is itself a Dirichlet process with a known form, which kind of describes a mixture between your base distribution, your p pi, and point masses at the observed data points. You actually get this, when C goes to 0, you end up converging to a Dirichlet process on the data itself. And what that means is that you can think of your posterior process, this limiting process, as a weighted sum of point masses where the weights themselves are random. So it's, if you think about your empirical CDF, that puts equal weight on all of the data points. So you get 1 on n for every observation, and that gives you a single curve. In a classical bootstrap, you would resample those data points with replacement. And so you would get multiples of 1 on n for some values, and you might get 0 for other values in your data. But that would give you a collection of different distribution functions, which we often, or frequentists often use to characterize their uncertainty in the distribution function itself. So Bayesian is going to do something similar, but this Bayesian bootstrap approach doesn't assume that, or doesn't just resample the data. We keep every data value included in our empirical function, but we change the weights. And it turns out, according to this, because of a representation of the Dirichlet process, the weights will actually have a Dirichlet 1-1-1-1 for as many observations as you have. And this is actually very easy to sample. You can sample, say, exponential 1, and then normalize those weights. So you take n exponential 1 IID draws, and then force them all to add up to 1. And that would give you one set of these weights, which would satisfy the representation here. So a Bayesian bootstrap is you repeat that sampling of the weights themselves, and that gives you uncertainty quantification or representation of the uncertainty you have in the true population given your data and given this limiting result as C goes to 0. The nice thing about it is a couple of things. One is you actually don't need to specify this p-pi at all because it gets wiped out by C going to 0 anyway. So that's one thing that is an advantage. You don't have to think too hard about the problem. The other thing is that when you do this replication of the simulation, you can just repeat this in independent using simple Monte Carlo. So you don't need any Markov chain Monte Carlo, which will make things a bit more demanding. So if you didn't want to let C go to 0, you could do the procedure we're talking about. You just need to do it inside an MCMC, Markov chain Monte Carlo setup. So by taking C equal to 0, we can just use simple Monte Carlo, very easy to parallelize, can happen very quickly. You can get a lot of draws in seconds. So what we do is we have our data, we have our Dirichlet process model with C going to 0. This defines a posterior, and thus it defines a distribution over the curve associated with the uncertain posterior. So we just repeat for little b, 1 up to big B, the bootstrap samples, sample the weights from a Dirichlet 1-1-1-1, which is, as I said, exponential, and then make sure the weights sum to 1. And then compute a path for each bootstrap replication, which is defined by now the finite sample weighted loss measure, expected loss. So you take expectation with respect to the weights here and minimize that function. So what we need to be able to do is, compute these mu b for the continuum lambda, and that gives us a different path for every bootstrap replication. So as I said, highly scalable, trivially parallelizable. I can't even say these words this morning. And then we estimate the probability of the null, say, by just checking how many of those paths satisfy the null and how many of those paths satisfy the alternative. Of course, by strong large numbers, these probabilities will converge as the number of bootstrap applications goes off to infinity. So, and we can make B as large as we like and get these probabilities to whatever precision we want. Okay, so let's just denote those posterior probabilities for the null and alternative as p hat h0 and p hat h1. And then the optimal decision will be to minimize whichever decision gives us the expected loss for the decision problem itself. So there's sort of two losses here. One is to get the curve for the Huber path for each bootstrap replication, and the other is to make the decision in, as I said, a standard Bayesian decision rule context, well-established standard method, nothing new here really. We're just applying it in this context, and we can have just two outcomes, a null and alternative, but we can also add other possibilities, such as define an indeterminate region, and just corresponding to what posterior probabilities we want to see appear to make that decision. So that's at the discretion of the analyst, but that's always reported, and you would just report the probabilities of calculating the null, calculating the alternative, and that would define all the probabilities. So if someone else wanted to use different loss functions here in L, they could simply adjust and calculate for themselves. So in what we've implemented in the paper, we're just doing simple 5% testing on both ends, and anything where if you don't have p hat h0 greater than 95%, well, that's when we would accept h0. We only accept h1 if p hat h1 is greater than 95%. Otherwise, it's indeterminate. So if we fall somewhere in between, we don't conclude either one. Okay, so that's how we build the test using the Dirichlet process. And now I just want to say for a minute about this path optimization problem. We actually have a proof in the paper that the method gives you the exact Huber path. And the idea is simply that once you realize that, if you think about univariate data, which is the easy case, then as you move from, say, the largest value in your data set and incrementally move down to the smallest value, so you're tracing from lambda infinity down to 0, you actually find that the Huber path is piecewise linear. And this is something that it's sort of known in the literature, but not in this context. So that was not easy to realize because there was other work that kind of picked up on this idea, as I say, in other settings. So the fact that we know that it's piecewise linear means we just have to find each of those points where the linearity changes. And that's easy to find. And we have, so that's what the algorithm does. I probably won't, because of time, go into too much detail there. The proof is in the paper if you're interested. I'll just show you what a path might look like. This is one particular path for that data set. So it starts off at the sample mean, and then depending on the weights, well, it's not actually the sample mean, it's the weighted sample mean, because it's going to depend on your bootstrapped weights that you've drawn in that replication. But it'll be the weighted sample mean. And then you can see that this function, as you move from right down to left, it moves around because the weights are whatever they are. And the function, that path, is piecewise linear. So we can easily find it. So then if we do this many, many times, we get a whole collection of these curves. And then we just check how many of them cross the null value wherever one is. It's not drawn here on this plot, but if one was up here, maybe near the top of this one particular curve, maybe a lot of the other paths don't cross one very often, and your probability of H0 might be quite small, for example. It also turns out that this optimization is related to the Lars algorithm, which is used to estimate, to implement a lasso in a linear model. Now, we are not fitting linear models here. We're just testing one location parameter, basically. I shouldn't call it location, center parameter, because it's a whole spectrum of parameters. But there's a connection between the Huber loss and what's called the Moreau envelope. And it's because of that connection that there's a connection between our optimization algorithm and the algorithm from the Lars algorithm, which some of you may know about, and maybe you don't, and that's fine. The one thing that I will say is that our algorithm is specialized for the particular case of just a single center. And for that reason, it's not exactly the same as the algorithm of Lars. It's similar, but it's not the same. And ours is much faster for the problem we're trying to address. So sort of an order of magnitude faster. So there's potential in future work that there will be more connections there. But at the moment, there is a connection, but it's sort of not worth using because we can beat the Lars algorithm with our algorithm for our special case. So in the paper, we go through a range of experiments where we do sort of simple testing of sort of like one sample testing. Is this one population center equal to 0 or not equal to 0? It doesn't really matter what value you pick. We've just done them all at 0. And then we look at a range of different tests for different true population distributions. So for the actual normal distribution, if the data really are normal 0, 1, well, you can see that most of the tests are very similar, but there are some differences in terms of, well, at least power. So we've got here, the Huber family is the solid black curve, and it sort of straddles between the student t-test, which is above with the green one, which is the Fisher sign test, and, oh no, that's the red one, the Wilcoxon sign rank test, and the sign test is below. But they're not that far apart. It's not a huge difference for if the data really were normal. But for other distributions, it's quite different. And that's, remember that the normal has just, the true population has a single point for its entire continuum of Huber paths in the true population. So it's sort of not the most exciting case. But if you had, say, a skewed distribution and it happened to be exponential 1, then you would get very different values depending on the data that you actually had. So what we're doing here is changing the value of the null value across the range and mapping out then sort of in the shaded area, it really corresponds to this. For the exponential 1 model, all of the values in the shaded region are considered the null hypothesis. Any one of them satisfies the constraint. And so different tests, if you do a t-test, you're not testing all of those, you're only testing one. If you do a Fisher sign or Wilcoxon test, again, you're only testing one center. So it's going to find the one, but it's not going to look at all the others. So you can see that the sort of power curves are shifted. Interestingly, they're all similarly sized at least at the boundaries of the null region. And I'll talk about that in a minute. Similarly, for log normal, you get quite different things. For Poisson, something different again. And this all comes down to the fact that we're testing all of the range. And so overall, we're controlling the rejection appropriately for what we want to do. The others, because they weren't set up that way, just don't do that. And so if you really are interested in the continuum of centers, you need a test, which will do the test for the continuum of centers. And I'll just make one more comment about this test, and it kind of relates to why we have this 5% level at the boundaries, because we're using 5% tests. It turns out that our test is actually related to what's known as an intersection union test. Now, it's been a long time since I studied these sorts of tests, but I remember, there were always two types. There's the union intersection, intersection union, and you can look this up in the Casella and Berger textbook, Statistical Inference, which at least at Monash is our sort of core third-year textbook for our undergraduates. And there's a small discussion in there about intersection union test, which is the less frequently used one. Most often we're looking at union intersection in frequentist testing anyway. But this intersection union test, which was developed by Berger, Roger Berger of Casella and Berger. And the idea here is that you're thinking of, or at least as it's presented in the Berger 1982, is you're thinking of different characteristics of your sample or of the population related to your sample, and you actually want to test whether all of those features are satisfied. Now, in the context of Berger's test, it's just a finite number of these features. It's not an infinite continuum, but he shows that for this setup where your null is that all of these aspects of your test are satisfied under the null, versus the alternative where at least one of them is not satisfied, then the scenario he describes in his paper is, maybe you're doing some manufacturing and you might have multiple attributes of the product you're producing, and you have to satisfy, your product needs to satisfy all the different stress tests. And so you want to make sure that if you reject one of them, you just throw away the product is not suitable. So that's the idea of the intersection in the alternative. And it turns out that our test fits this framework because although it's not a finite number of attributes, we are testing a null where we want any one of our centers to be the null. Doesn't have to be all of them, just any one of them. And in the alternative, we're saying none of them are in the null set. So here it's the complement of the null value in the alternative. So that's, we believe, why, because it can be proven, and Berger proves it, that these types of tests will always control the overall type 1 error rate. They may not have high power all the time, but they are at least correctly sized. Okay, finally, I just want to mention a couple of examples, case studies, So in the paper, there are two, and neither one of them are at all related to finance. But I hope that you can see that really this is a general thing. It's going to apply in all kinds of different disciplines. And I did put in a behavioral finance example at the end, which I'll briefly mention. Just to be good friends. So the first example in the paper is relates to this study of body posture and whether you stay attentive. So if you stand up, do you respond more quickly versus if you are sort of not sitting properly, then maybe you're not paying attention as much. So it's a sort of well-known data set, and others have analyzed it. And so it turns out that for the t-test, for the sign test, the sign rank test, and for our familial test, you always get the same answer, and you accept the alternative. I like to say, do not accept the null or reject the null. But anyway, we're saying accept the alternative because it's a Bayesian test. So it turns out in this case, the result is robust to the choice of center. And that's reassuring, because if that is in fact the conclusion you want to make, it's nice to know that it doesn't really matter which version of center you use, you're always going to come up with the same answer. Now you might say, well, we got that answer from these other three tests. But of course, there's issues to do with, when you're doing multiple tests, what do you do about do you adjust for the number of different tests? Well, if you put it in the intersection union framework, maybe you don't need to. But it's not that we really only have 3 possible centers. We have a whole infinite number of them. So it is more appropriate then to do the familial test, we argue. A second example in the paper is multitask. So it's how attentive are you if you have to do different tasks at the same time. So you're slower if you try and they say nobody can multitask really. It's when you change from one attentive thing to another, you lose something like 40% of your reaction time or something. Anyway, so that's what I saw on Show About Your Brain not long ago. Anyway, in this particular study, it's a 2-sample test, and the t-test, you would reject the null or accept H1. The median and the rank sum would not reject the null. So you get conflicting answers depending on which frequentist test you use. And in this case, the familial test is actually indeterminate. Now, it would be the case that as you increase your sample size, you could still have a t-test, rejecting H0, and you could still have the median and rank sum not rejecting H0, but the familial test could conclude H1 or H0 depending. So it's not necessarily the case that just when you get some conflicting answers, you get an indeterminate result. It just happened to be that way in this example. So the final example I'll just mention is a randomized experiment. This is a behavioral finance question that has to do with trying to study myopic loss aversion in school children. So there's this study that's reported in this 2015 paper. I have no idea how to pronounce these names, so I'm not going to try. And they set up a designed experiment, and they have actually a couple of different controls. We've looked at 2 versions of these comparisons that they do and apply the familial test. So they're looking at, in the first instance, looking at children aged 11 to 17 in this cut of the data. And the children in one group are told to take a short strategy. Children in another group take a long strategy, and then they assess the performance of their portfolio and their response, how they feel about it, and you get different results. So this is kind of nice. Again, there's not necessarily any reason why you would have a well-defined center in this context. You could look at a different cut of the data and do the same approach. So this is, again, behavioral finance. There's lots of say a little bit about our future work, and then hopefully there'll be time for questions. We just got reviews back, and they were positive but demanding. So we have a lot that we need to satisfy them. So this is what we're currently working on. So we're looking at some multimodal distributions, consider multivariate data, not high dimensional, but more than just univariate. We actually have a proof of consistency, but we didn't put it in the paper. So we're working on making that a little more palatable, I guess. They want us to say, how would a frequentist do this? And actually, I think the intersection union test is the way we're going to proceed at the moment on that. And of course, they want us to do all that and shorten the paper. So there'll be an online supplement, I'm sure. And we're also working on extending this to a linear model. And finally, we're going to start getting to the kinds of problems in finance that I would really like to get to. Because if you think about, say, Fama French portfolios and testing, coefficients, are they, is the beta 1 coefficient really 1? Well, in finance, maybe it makes sense to think about expectations. But on the other hand, it would be nice to understand better what that Huber path is for even in a finance context, I would argue. The other thing that holds us back in the finance setting, in the sort of looking at asset prices at least, is that we don't really anticipate we have IID returns or anything. So we really need to be able to incorporate dependency in this model. And at the moment, the Dirichlet process does not allow that. Given the underlying population, your data is assumed to be IID. However, one of the co-authors, Steve McEachern, is really the person who initiated the whole strand of the literature on dependent Dirichlet processes, which would be suitable for this question. So we're not there yet, but that's where we're going. So thanks very much for your attention, and I'm happy to answer any questions if we have time.
Thank you, for Professor Forbes. It's a wonderful talk.
Thank you.
Now, anybody have any questions, comments? If there are no questions, I have one comment and a couple of questions. So
Sure.
one comment is that, about 3 years back, I kind of gave up on the Dirichlet process prior.
Okay.
CMC doesn't work.
Okay.
I mean, I have tried many ways, and it only works in toy examples, but when I try in my data, it never converges. But that was my experience. But I now, having a kind of seeing your work and Bayesian bootstrap, just, it lights the bulb in my,
Yeah.
mind that, why didn't I try that? So definitely I will try that. So it's a really nice, I think, approach that you have taken, and I think it should work. It's a simple and it should work. I mean, so definitely
Yeah.
I try.
Great.
So that was my comment, and I have two questions. One is, when we are doing Bayesian testing, generally the first thing that comes in my mind is the Bayes factor. So have you tried in this paper to calculate the Bayes factor? That was one. And the second thing is, there is another approach which is a little bit less popular, is think of, you think of developing a posterior distribution over null and posterior distribution over alternative, and then take a sort of a kind of a Kullback-Lapland divergence, or the distance between the two distribution. So can that kind of approach be adopted in this, of course, in the future work in the familial inference? I would like to know your thoughts.
Yeah. So there, on the first question about the Bayes factor, because effectively this letting C go to 0 is like putting an improper prior on your model, on the parameters. And so Bayes factor is not well defined, in which case you can't really use it for testing. So the alternative strand in the Bayesian literature is to do a test, but think of a simple, even a parametric test where you're testing the mean is equal to, say, 0. You could put a, just put a continuous prior over that range, and then you wouldn't be able to test the point null, but you could test, are you in a region around 0? What's the probability that your practical region is around 0? And we also have priors where you put a point mass on the point, so like spike and then a slab on the rest of the distribution. You can do that sort of thing, and that's more the analog of what we're doing here. So that's, yeah, you can't really do Bayes factors directly. In terms of the Kullback-Leibler divergence, I think that, you know, under this model, you have a posterior that's well defined. So as long as you have data, your posterior is proper and well defined. And because you just get distribution of probabilities over the individual observations. And so you can map those distributions to any measure of that, any summary measure of that distribution. So if you're interested in, say, a measure of divergence, it would map into that measure. So just like any transformation of a random variable into a function of the random variable, it's the same process. But you would just do it numerically because you have, you know, the sampled weights, you have your empirical function, weighted empirical function for that bootstrap draw. You would calculate the corresponding divergence, and then you would get a sample of all of those divergence metrics. And that would be a sample from the distribution of the divergence metric, given the data.
Thank you. Thank you. I have just one quick comment that since you're already thinking about Fama-French model, it's essentially a simple linear regression for us.
Exactly. Yeah.
So I think instead of testing for beta equal to 1, be more, you know, attractive if you test for alpha equal to 0, because alpha equal to 0 means that the market is efficient, but if it is non-zero, that means market is not efficient. So I think, you know, I had a small stint of, you know, working in the industry at that time. I found that, you know, alpha equal to 0 is more exciting for the, you know, market players than the beta equal to 1 or not 1. So I thought just I will mention.
Yeah. No, thank you. Thank you. That's it. I will try to.
And actually,
that one instead.
my colleague Ritu and I, we wrote also a paper on that, on Bayesian multiple testing on alpha.
Okay.
So I'll maybe share that with
that would be great. Yeah.
Maybe that will be helpful to you.
Thanks very much. That would be wonderful.
Yeah, extending. I think your familial inference is a natural extension to that work, because essentially it's a multivariate. I mean, Fama-French model is a multivariate regression, simple multivariate regression problem. And I can see it's a natural extension to that.
Yes, great. Thank you. That's wonderful. I would really like to see it.
Sure. Any more questions for Professor Forbes? If not, then I would say that, you know, now this session is closed, and we will again come back at 5:30 Indian Standard Time. So thank you all very much, and see you soon.